Good afternoon. I'm John Anderson, President of the National Academy of Engineering, and welcome to Engineers Week. This week, we celebrate engineers whose creativity, innovations, and technological advancements shape our world. Engineers think big. They create awe-inspiring innovations. They push innovation and make revolutionary changes. They find solutions to today's challenges. They visualize a future of possibilities, and they create the technologies and products that shape our lives, things we didn't know we needed, but now we can't do without. From life-saving vaccines to space travel to our global connectedness through the World Wide Web, engineering touches every facet of our lives, and engineers make it all possible. With me today is Dr. Stuart Parkin, the 2024 winner of the Charles Stark Draper Prize for Engineering and member of the U.S. National Academy of Engineering. Dr. Parkin is director of the Max Planck Institute of Microstructure Physics in Halle, Germany, and an Alexander von Humboldt professor at Martin Luther University, Halle-Wittenberg. His research interests include spintronic materials and devices for advanced sensor, memory, and logic applications, exotic superconductors, and cognitive devices. Dr. Parkin's discoveries in spintronics enabled a more than 1,000-fold increase in the storage capacity of magnetic disk drives. In short, his work has facilitated the big data world we live in today. Dr. Parkin is being recognized with one of the world's most preeminent awards for engineering achievement, the Charles Stark Draper Prize for Engineering. Named after engineering pioneer Charles Stark Doc Draper, the Draper Prize for Engineering honors an engineer whose accomplishments have significantly impacted society by improving the quality of life, providing the ability to live freely and comfortably, and permitting access to information. Let's take a quick look at the Draper Prize, the man who established the prize, Dr. Draper, and the innovations and accomplishments of this year's recipient, Dr. Stuart Parkin.
The Charles Stark Draper Prize for Engineering was established by the National Academy of Engineering and endowed by the Charles Stark Draper Laboratory Incorporated in 1988 to honor the memory of Doc Draper, the father of inertial navigation, and to increase public understanding of the contributions of engineering to the freedom and well-being of humanity. The prize recognizes engineers responsible for technological developments that have transformed modern life. Doc Draper was an educator who trained generations of students at MIT. His belief that education needed a hands-on component led him to establish the instrumentation laboratory within MIT's aeronautics department. In 1973, MIT divested the laboratory, thus creating Draper, an independent, not-for-profit engineering solutions company. The Draper Prize acknowledges working solutions rather than theoretical discoveries. Examples of past winners include the developers of controlled drug delivery systems, creators of the GPS, inventors of the cell phone, innovators in wireless communications, and pioneers of personal computers and the Internet. Without these remarkable engineering achievements, much that we take for granted in our day-to-day lives would not exist. The 2024 Draper Prize is awarded to Dr. Stuart Parkin for engineering spintronic technologies, enabling digital information storage that serves as a foundation for today's data-driven world. Spin electronics, or spintronics, goes beyond conventional charge-based devices and technologies and makes use of a quantum mechanical phenomenon that has unique properties, the electron spin. In the mid-1990s, Parkin demonstrated a sensing device that detected the magnetic spin of electrons, making it possible to manufacture hard disk drives that could store and read thousands of times the amount of data than before. Spintronics technologies opened up the possibilities to construct non-volatile memory storage devices with high storage density, low power consumption, and fast operation that are inexpensive and robust. Dr. Parkin is an experimental physicist and director at the Max Planck Institute of Microstructure Physics in Halle, Germany, and an Alexander von Humboldt professor at the Institute of Physics of the Martin Luther University, Halle-Wittenberg, Germany. His research interests include spintronic materials and devices for advanced sensor, memory, and logic applications, oxide thin film heterostructures, topological metals, exotic superconductors, and cognitive devices. Parkin was elected to the NAE in 2009, and he is also an elected fellow or member of 7 professional science and engineering societies, including the Royal Society, Royal Academy of Engineering, National Academy of Sciences, and the German National Academy of Science Leopoldina. Parkin has received 4 honorary doctorates, published more than 685 papers, holds more than 126 patents, and has given approximately 1,000 invited talks around the world. Today, more than 70% of all data is stored in massive arrays of magnetic disk drives, each of which uses Parkin's spintronic reading devices. These vast digital server libraries, often called cloud storage, allow for universal access to information. Social networking tools, the world's libraries, music and films, and advances in many fields such as public health, internet banking, e-commerce, logistics, and surveillance are also made possible by the enormous data storage capacity of these spintronic devices. In recognition of these innovations that have transformed our world, we award Dr. Stuart Parkin the 2024 Charles Stark Draper Prize for Engineering.
Now we'll hear from Dr. Parkin, who will discuss spintronics for massive data memory storage, past, present, and future. Following his presentation, NAE Executive Officer Al Romig will hold an informal question and answer session. The webinar will close at about 2 p.m. Dr. Parkin, welcome.
Thank you. Let me share my screen. And hopefully that's working. Well, okay, good morning. Thank you very much for that kind introduction. And of course, I'm extremely honored to have been awarded the Charles Stark Draper Prize. And I'd like to tell you in the next few minutes something about spintronics, which enables massive data memory storage. And I want to discuss briefly the past, the present, and the future. And in this first of all, you can see a drone video of some of the laboratories that my colleagues have built at the Max Planck Institute in Halle, Germany, since I moved there in 2015. And these systems are needed to build the exotic magnetic heterostructures that enable spintronics. On the right-hand side, you can see in this schematic cartoon, blue and gray and red layers, each one representing 1 to a few atomic layers of magnetic and non-magnetic materials. And by developing these magnetic heterostructures, we can build devices that have properties unlike any other material. And in particular, they can be used technologically. And I'm going to briefly discuss how we have used these devices to enable massive digital data storage. First, let me show you this foil where let's first talk about computing technologies. And over the last century, computing technologies have increased in power exponentially. And this has been made possible by a series of distinct devices that lasted typically 2 or 3 decades. For the last 4 decades, the computing systems are powered by CMOS electronics. These are charge-based storage devices and charge-based transistor computing devices. However, the concept behind the current day technology involves shrinking the transistor systematically every 2 years by a factor of 2 for the last 4 decades. It's enabled enormous increases in computing power, but at the same time, we now recognize that this roadmap has come to the end of its roadmap, and we need to do something beyond charge-based electronics. And we can imagine different ways of computing that goes beyond using the concepts of today, which are essentially binary computing. We could imagine cognitive computing. Cognitive computing is a concept that our brains are approximately 1,000,000 times more energy efficient per computing operation than today's silicon-based computing systems. This is one possibility. Another possibility is to develop quantum computing systems. This is very exciting today and has a huge potential. In a quantum computing system, a single device has multiple states, enabling in principle, exponential advances in computing power. These might, of course, take some time before they become realistic. Therefore, in some sense, we want to go beyond the concept of charge, where we today use certain numbers of electrons in a capacitor as a memory element, or we control the passage of currents of electrons in a transistor. Can we go beyond using the electron's charge to use, for example, the electron spin? This is the topic of my talk today. At the same time, we can also imagine building devices that more reflect that of the structure of the brain, for example, by controlling currents of ions. This is an interest of mine, but I'm not going to discuss this today. And then I think another very important concept is that nearly all of today's computing and memory and storage devices are innately two-dimensional. Either in silicon-based devices, you have a two-dimensional array of transistors in the surface of a highly perfect silicon crystal structure, or alternatively, as I'm going to briefly discuss, in a magnetic disk drive, you store information in a two-dimensional magnetic film. So can we go beyond this to build three-dimensional devices? And towards the end of my talk, I'd like to discuss something about my own concept for a three-dimensional racetrack memory. Now let's go back in history, approximately 550 years. And in Germany, in the city of Mainz, Johannes Gutenberg spent several years developing a very interesting technology. This was the movable type press. And he invented many aspects of this technology, and in particular, even the material that enabled him to build this movable type. This was a lead, tin, antimony alloy, which has been used for the last 550 years. So this was a remarkable achievement. What did it allow? It meant that instead of writing by hand on a piece of paper with a quill pen, one could print books. And of course, what this meant was that knowledge and information was no longer confined to a small group of people. It could spread. And this led essentially to the age of the Enlightenment, where knowledge could be accessed by more and more people. Well, this age of analog book printing lasted approximately 550 years. 70 years ago, in San Jose, California, IBM invented a new technology, the magnetic disk drive, and it's shown here in the middle of this foil. The magnetic disk drive is a mechanical device, pretty much like a record player. Of course, record players are no longer used by many of us. Nevertheless, the concept is you have a glass disc which is rotated at high speed. On the surface of this disc is a thin magnetic film, and the magnetic film is magnetized in tiny regions. The magnetic moment direction today is either perpendicular up or perpendicular down to that glass layer, to that magnetic film. And then on top of the surface of this magnetic film is a reading and writing device, which is moved laterally over the surface of the rotating disk to both write and to read the digitally encoded information. On the left-hand side, you can see an image of some of these magnetic disks shown as white and black regions, magnetic moment pointing up or pointing down. And you can see as from the right to the left, these regions are being shrunk in size. And over the last 70 years, these regions have shrunk by many orders of magnitude. That means we need new means of both writing and reading this information. And I want to tell you how I was able to invent a technology that enabled the size of these magnetic regions to be decreased by more than 1,000 times, enabling the storage capacity of magnetic disk drive to be increased by 1,000 or even 10,000 times in the last few years. What does this mean? Today, we're very familiar with the cloud. Today, if you look inside the cloud, what you will see, of course, are computing systems, but at the same time, you will see enormous numbers of magnetic disk drives, which, as John said in his introduction, store today 70% of all digital data. And this is, in essence, is the lifeblood of many companies which have only evolved over the last 15 years or so, including Facebook and Google, Microsoft, and others, which take advantage of the enormous quantities of data that can be stored in these magnetic disk drives. We live truly in a digital world today. This can be reflected, for example, in how we store data. I think this is a very nice paper. It's more than 10 years old, but it reflects an important turning point. The two authors of this paper explore how data was stored in a 2-decade period. And the colors in orange represent analog means of storing data, for example, in a book. And the blue represents digital means, where the data is stored as a series of zeros and ones, as in a magnetic disk drive. And approximately in 2007, the storage of digital data exceeded that of analog data. I'm going to come back to that in a moment. Of course, today, all data is essentially digital. And how was this made possible? This is made possible by taking advantage of a very interesting property of the electron, its spin. The spin of the electron is a quantum mechanical property. This means it can only take two values. The spin either points up or it points down. And we can take advantage of that electron spin to create materials in which we control the creation, passage, and detection of the spin polarization of the electron. And I'd like to give you a simple example of how we can do that. Let's take, for example, a metallic conductor like copper. In copper, if we introduce current from a battery, as shown on the left-hand side in this cartoon, the battery will produce electrons, equal numbers of spin up and spin down. So in the metallic material, which is non-magnetic, the current will be carried equally by electrons with spin up and spin down. All the electrons will be scattered at the same rate. And of course, how they scatter will determine the resistance of the device. Let's take a different example. In this example, the material is no longer non-magnetic. This is a magnetic material. At room temperature, this could be iron, could be cobalt, it could be nickel, or it could be some combination of those materials. When we introduce current from a battery on the left-hand side, then the current will, within a few scattering lengths of the electrons, become spin polarized. That means the current will be carried predominantly by electrons of one spin orientation. So let's say in this material, well, let's color code it blue. The magnetization points to your right, and the electrical current now will be carried predominantly by electrons whose spins are oriented in the blue direction, parallel to the magnetic moment of the material. Now let's take the example where we build on the atomic scale a multi-layered sandwich, a sandwich consisting of two magnetic layers, shown here as red and blue, separated by a thin non-magnetic layer. This would be copper. Now, when we introduce current from a battery on the left-hand side, in the blue layer on the bottom, just as before, the current will be carried by electrons whose spin is in the blue direction. But in the red layer, the current will be carried by electrons with a spin in the opposite direction because it's magnetized in the opposite direction, as shown by these white arrows. However, if we make the copper layer sufficiently thin and the magnetic layers sufficiently thin, then the blue electrons will cross from the lower blue electrode through the copper layer into the red layer, where they will be scattered, and the scattering rate will be stronger because they're now in a material in which the blue electrons are strongly scattered. And vice versa, the red electrons from the top layer can pass through the copper layer into the blue layer, and then they will be strongly scattered. So in this material, in this configuration of the two magnetic layers in this sandwich, the electrons introduced from the left-hand side will be scattered strongly everywhere, somewhere in this structure. Now let's do something very simple. We rotate the magnetic moment direction of the top layer so it's pointing to the right in the same direction as the bottom magnetic layer. Now, in this case, when we introduce current, then the blue electrons are favored in all these layers, and so they can essentially short-circuit the current through this sandwich. And we've created what we called a spin valve. The valve turns on and off current by taking advantage of the spin polarization of the current and its relatively stronger scattering rate for one spin orientation compared to the other. So the resistance of the top layer, the top structure in which the magnetic moments are anti-parallel to one another, will be higher than the bottom configuration of the magnetic moments when they're parallel to one another. And so this means that the resistance of this device can be changed by an external magnetic field, which changes the relative orientation of these two layers. So we can build a sensing device. And it turns out when we properly spin engineer this device for maximum sensitivity, we demonstrated that this type of spin valve sensing device can sense magnetic fields at room temperature 1,000 times more sensitively than any other device at room temperature. So this enabled us to introduce this sensing device into a magnetic disk drive and detect magnetic regions, the magnetic bits, 1,000 times smaller than was previously possible. In reality, in the sensing configuration, the magnetic moments of the two layers are designed to be orthogonal to one another. This gives rise to a maximal change in resistance in the presence of small magnetic fields. And another very important characteristic of these structures is that a magnetic moment will give rise to dipole stray fields. And in this configuration shown on the top, the stray fields from the lower layer will be attractive to the upper layer, and it lowers the energy of the system. So to build actual sensing devices on the nanoscale, which is required to detect tiny magnetic regions, we need to eliminate these fringing fields. Otherwise, the magnetic moments will always be oriented anti-parallel to another when the device is scaled to nanoscopic dimensions. And I invented something called a synthetic antiferromagnet that makes that possible to eliminate all stray fields. I'm going to discuss that a little bit later in my presentation. So what does this mean? If we now introduce this spin valve sensing device into a magnetic disk drive, and this happened in 1997 by IBM, where I worked at the time, this enabled the numbers of magnetic regions, or the bits per unit area in a magnetic disk drive, to increase dramatically faster than was possible before. And this is shown in the bottom left picture of how the areal density, the numbers of gigabits that could be stored per square inch in a magnetic film, in a magnetic disk drive, evolved as a function of time. And you can see after IBM introduced the spin valve head, they could increase the areal density 100% per year for several years, dramatically improving the storage capacity of these magnetic disk drives. And this has meant then that the magnetic disk drives today can store all information that we create, which is extremely important for today's digital world. Now, it turns out that the spin valve sensing device, based on this concept of spin-dependent scattering, first, let me point out that the spin-dependent scattering in that spin valve sandwich mostly takes place at the interfaces. This enabled us to shrink the thicknesses of these magnetic layers to minuscule dimensions, which enabled, again, the ability to detect tiny magnetic regions. So the interfacial characteristic of the spin-dependent scattering was incredibly important. Now, the technology, the spin valve sensing technology based on spin-dependent scattering, evolved after 10 years to essentially the same structures, the same spin valves, but the physics evolved from spin-dependent scattering to spin-dependent tunneling. Now, spin-dependent tunneling was a concept known about from the 1980s. In this concept, as shown in this schematic cartoon, you can see, again, we have two magnetic layers, shown by their directions, red and blue, but the gray region in between the layers is no longer a metal like copper, it's actually an insulator. And the electrons have to quantum mechanically tunnel from one magnetic layer through the tunneling barrier into the opposing electrode. When the magnetic layers are parallel, the electrons that are extracted from one surface will automatically be spin polarized. This is because in a ferromagnet, the number of electronic filled states at the Fermi level is distinct for spin up and spin down electrons. The symmetry is broken by the magnetic moment of the system. So the electrons automatically that are tunneling are spin polarized, but they have defined states on the opposite side of the tunneling barrier which have the same spin polarization. This is only possible when the magnetic moments are parallel to one another. When the magnetic moment on the right-hand side is reversed, becoming blue, then the electrons tunneling of the red characteristic find only states of the blue states to tunnel into, and that's not possible. The electron spin is conserved in this tunneling process. This leads to a dramatic increase in resistance in the lower configuration. And indeed, the change in resistance for this type of tunnel junctions can be several 100% at room temperature. And this is something that I showed in a paper I published in Nature Materials in 2004. And this was a breakthrough that made possible the use of these tunneling junction devices as spin valve sensors based on spin-dependent tunneling. And this enabled, again, further increases in the storage capacity in a magnetic disk drive. However, this is then shown here. This is how the evolution as a function of time of the tunneling magnetoresistance, which I just discussed, versus the spin valve magnetoresistance evolved. And you can see the spin valve magnetoresistance at room temperature is relatively small, a few tens of percent, but the tunneling magnetoresistance can be hundreds of percent. In 2001, I showed this 220% at room temperature was possible. The change in resistance between the high resistance and low resistance state at room temperature. And today one can achieve even higher changes in the resistance of this material. This is useful for building advanced sensing devices. Now, when you build a tunneling device, what is critical is the thickness of the tunnel barrier. That will determine the resistance of the device. And at useful dimensions today, that means the tunnel barrier has to be less than 1 nanometer thick. And the so-called resistance area product has to be extremely tiny. And we have been able to achieve resistance area products lower than was ever possible before in any type of tunneling junction device. So this was a very important achievement. And this was by using a combination of a magnesium oxide tunnel barrier connected to a particular magnetic layer that has a particular configuration, a body-centered cubic configuration, in which the electrons extracted from the magnetic surface are spin filtered through the tunneling barrier to enable extremely high spin polarizations of the current. And we've achieved spin polarizations of more than 95%. This enables these huge changes in tunneling magnetoresistance. So then what happens? We could use this tunneling junction principal device in a spin valve configuration to read information in a magnetic disk drive. And these tunnel junction spin valve devices have been used since 2007 in magnetic disk drives. However, at the same time, one could use the same magnetic tunneling junction as a memory element. Here you store information in the direction of the magnetic moment of one of the magnetic electrodes. So shown here, the right magnetic film is magnetized to the right or to the left, red and blue. And we design a device so that the magnetic orientation of these layers will be retained for up to 10 years at room temperature and above, in fact, up to temperatures as high as 150 degrees centigrade. So this can be a memory device. And because of the very large change in tunneling resistance, one could read the state of this memory device very, very quickly. This is something that we actually proposed in 1995. This is a picture I've taken from a review article I wrote in 2015. The concept is that you have a set of wires pointing in horizontal in pointing to the left, up and down in a cross-point configuration. The tunnel junction is placed between these layers together with a transistor to access an individual device. So let me just give you a brief overview of the history of the magnetic tunnel junction-based MRAM. It's something that we proposed with my colleagues, in particular Bill Gallagher at IBM Yorktown Heights Research Center in 1995. And we were very fortunate to get funding from DARPA to build, to see whether we could develop this tunnel junction magnetic random access memory. When we first started, the tunneling magnetoresistance of such tunnel junction materials at room temperature was just a few percent, not sufficient to create an interesting memory. However, within just 3 or 4 years, we could demonstrate using conventional tunnel barriers, tunneling magnetoresistance values of more than 80% at room temperature. And later on, we further developed the tunneling magnetoresistance values, as I briefly mentioned, to more than several 100% at room temperature. This makes it possible to read the state of these tunnel junction elements extremely quickly. Here is a cross-sectional view of a tunnel junction device built into an array, a cross-point array, where you can see the metal lines across from left to right and from out of this foil in this case. So this is two metallic layers. The tunnel junction is placed in between these layers and is accessed through a transistor device. This was a fully functioning 16 megabit MRAM chip that myself and my colleagues developed in 2005. Then it took some more time before major semiconductor companies were interested. But since 2019, magnetic random access memory has been widely available, and it has already replaced one important memory family of memory, which is the embedded dynamic random access memory. And it's set to replace memory in all microcontrollers, for example, in electric cars in the next couple of years. So altogether, the amount of MRAM sold has already exceeded several $1 billion. So I think this is another major success of a spintronic technology. And I want to point out this second technology is also innately two-dimensional. If you look in this cross-section of this MRAM chip, basically we use a series of transistors built into the surface of silicon that restricts us to a two-dimensional array of tunnel junction devices. Similarly, the magnetic disk drive is a two-dimensional film in which we store magnetic bits. How can we go beyond these concepts? So let me just, before I come to that, I just wanted to point out that to introduce the spin valve, it took a relatively short period of time, only a few years from the basic discovery of the materials, cobalt and copper, the ability to create artificially engineered structures of particular the synthetic antiferromagnet, the concept of interfacial spin-dependent scattering or dusting layers. All of these concepts enabled the spin valve sensing device to be introduced by IBM in 1997 and by all other companies within a couple of years. As I mentioned, that technology, the basic structures remained the same, but the physics switched from spin-dependent scattering to spin-dependent tunneling in 2007. Today, the magnetic disk drives, whilst they're super important, the ability to increase further their storage capacity has slowed significantly, and alternatives are needed. Magnetic random access memory has taken more than 20 years from the proposal in 1995 to widespread adoption in 2019 and beyond. This took a lot longer because you need arrays of billions of devices that operate with high precision and accuracy, whereas in a spin valve device, you need individual devices. This is a more straightforward use of this technology. Now let me switch to this concept of a 3D memory. And I want to show you how we could potentially do that. To do this, we want to use another property of the electron spin. As I mentioned before, if you pass current into a magnetic material, automatically the current becomes spin polarized. Now, if you have a magnetic material shown in the bottom, where you have a region where in the magnetic material, let's say this is a wire, where the magnetic moment of the material points to the right. You can see this in the left-hand orange region. And in the right-hand orange region, the magnetic moments point to the left. In between, you have what is called a magnetic domain wall, where the magnetization switches from one direction to the other. And on the nanoscopic scale, this domain wall looks like an entity. It looks like a particle with mass and momentum. But now, if we introduce current into this system with magnetic domain walls, the current you can see as the moving electron with spin will, as it crosses the domain wall, adiabatically transfer its spin angular momentum to the fixed magnetic moments in the domain wall, causing them to rotate and the domain wall to move if sufficient numbers of electrons and their spin angular momentum are transferred into the domain wall. Now, it turns out this is a very efficient process. Nearly 100% of the spin angular momentum carried by the spin polarized electrons can be transferred to the magnetic system. And this kind of physics allows the domain walls to be moved at speeds of about 100 meters per second. So my proposal was we could build a vertical racetrack, a magnetic wire shown in the right-hand side, where the magnetic wire is of uniform composition, but is magnetized in the two directions, blue and red. And in between these regions, there is a domain wall. The presence or absence of the domain wall will correspond to a 0 and to a 1. More importantly, by simply passing current pulses into the racetrack, all the walls will move according to the principle I just discussed for a single domain wall. But the point is, since the current is automatically polarized in a red or blue direction, all the walls in principle should move in the same direction. Therefore, we can move our digital data around the racetrack and bring it to, for example, a reading element. This could be a magnetic tunneling junction embedded in the racetrack, or it can be brought to a writing element where we could write the domain walls into the racetrack. And this means that in an area of silicon where we store 1 bit in today's charge-based memory devices, or in a magnetic tunnel junction-based magnetic random access memory, we can now store perhaps 100 domain walls in a vertical racetrack, enabling a 100-fold increase in storage capacity. This is the concept that I proposed in 2002. It's taken all this time to prove that the concept really is technologically viable. I want to show you briefly. So over the last period of time since 2002, I guess that's 20 years, we've gone through a series of different racetrack iterations shown here. I don't have time to discuss all of these. The most important one is this racetrack family, which we call 4.0. This racetrack, as I briefly mentioned earlier, we have to avoid all the magnetic stray fields emanating from the domain walls, just as they emanate from the transitions between magnetic regions in a magnetic disk drive, allowing them to be detected by a spin valve sensor. Here we want to eliminate all these stray magnetic fields, otherwise they will cause interactions between neighboring domain walls in a single racetrack or between neighboring racetracks, which would have to be packed closely together to build a memory device that could have the capacity of a magnetic disk drive. That is the objective. And we believe today that we've demonstrated we can move a series of domain walls in these so-called synthetic anti-ferromagnetic racetrack at speeds exceeding 1 kilometer per second, 10 times higher than was possible 20 years ago when we started. So in 2008, we demonstrated for the first time that using the principle I discussed, the spin transfer of angular momentum from spin polarized current passing through a magnetic film, we could move a series of domain walls together. But the speed was limited by the amount of spin angular momentum from the current. Today, we have alternative methods of creating spin polarized current or pure spin currents by passing current through neighboring layers. In this cartoon, it's shown as this yellow layer. This is a heavy metal like platinum or tungsten, in which the electrical charge current is converted to a transverse spin current through a very different principle of so-called a spin Hall effect. And the spin currents diffuse into the synthetic anti-ferromagnetic racetrack, and they provide angular momentum and provide torques on the domain walls to cause them to move. But this is much more efficient, 10 times more efficient than in racetrack version 1.0. So today we can manipulate and move the domain walls even more efficiently than we could imagine 20 years ago. This is what makes it a very exciting technology. It's better today than 20 years ago when I first proposed this. And let me just show you, most of our physics, the physics to explore materials, is accomplished by using optical detection methods. So in the top of this foil, you can see a racetrack which is 3 microns wide, and the black and gray regions correspond to magnetic moment pointing out of the foil or into the foil, and the domain walls are in between these black and gray regions. We pass nanosecond long current pulses into the racetrack, and you can see all the domain walls moving together to the right and then to the left as we reverse the current direction in the pulses. And in the lower figure, you can see images of domain walls moving in a synthetic anti-ferromagnetic racetrack at speeds of more than 1 kilometer per second by introducing current pulses. So the physics is a rather complex interplay of four spin-orbit-derived phenomena that I won't have time to discuss, but most importantly, these domain walls actually have a chiral spin structure. This is key to their motion in the same direction under the influence of spin currents derived from the spin Hall effect. On the right-hand side, you can see in a cartoon form the structure of the simplest racetrack. In the top, the racetrack is a simple ferromagnetic racetrack, and the racetrack itself is composed of the green and blue layers. These are formed from cobalt and nickel layers, each one just 1 to a few atomic layers thick, a few angstroms of cobalt, a few angstroms of nickel, a few angstroms of cobalt. This makes the racetrack. It's 1 nanometer thick. And underneath, you have some metal layers. In the bottom, you can see a cartoon, the same racetrack, with the blue and green and blue layer, cobalt, nickel, cobalt, but it's separated. The two racetracks are identical. The lower racetrack and the upper racetrack, they're separated by this yellow layer, which is formed from ruthenium. And in the early days of spin valve, when I was working on spin valves, I discovered a long-range oscillatory coupling through all the transition metals and noble metals in the periodic table. And by choosing the proper thickness of ruthenium, this leads to an extremely strong anti-ferromagnetic coupling, so that the magnetization in the lower racetrack, for example, this blue region, will be exactly mirror imaged by the same moment in the opposite direction in the upper racetrack, meaning in aggregate there's no net magnetization. Therefore, we've eliminated all the dipole fields. And this concept of a synthetic antiferromagnet was also used in IBM's very first spin valves. It's the only way to build nanoscopic magnetic devices. Otherwise, they have too strong magnetic interactions through these dipole fields. This is just to point out that in order to build these structures, we need to use techniques that enable us to deposit angstrom thick layers over very large wafers, 300 millimeter wafers, to build racetrack memory technology. And this is possible using simple techniques, a technique called sputter deposition. And this is something that I used on the very first spin valve sensing devices. And I'm just showing you here an image picture of the system that I built in my new institute in Germany. And on the left-hand side, you can see a tube. This is in orange. It's 15 meters long. It's an ultra-high vacuum tube in which we've designed and built robotic systems that enable us to automatically transfer by computer control a substrate, a wafer, onto which we will deposit the atomically thin layers. But now we can transfer these wafers from between different ultra-high vacuum systems. In particular, one we call Mango. This is homemade, but it's a very sophisticated system in which we can have up to 44 different sources of materials to deposit different types of elements or compositions or compounds in this way at temperatures up to 900 degrees centigrade. And then we can take a wafer from Mango and we can place it into a molecular beam epitaxy system or into a pulsed laser deposition system. These are different techniques designed to deposit different types of materials with greater efficiency than otherwise would be possible. And we could also now exfoliate in a glove box 2D materials. And so we can create Van der Waals materials. We can create very complex heterostructures and explore their properties. And we can, by design, then create materials that have properties that are suitable both to explore physics and to engineer materials for applications in memory and storage. So if there's just a few moments left, I want to briefly then say now recently we've gone beyond optical techniques to detect domain walls. And now we're using something called the anomalous Hall conductivity. What does this mean? This simply means, as shown in this cartoon, that if we have a magnetic material, when we pass current through that material, the current, the electrons, will be scattered from the magnetic moments and will be scattered preferentially to the left if the magnetization, let's say, is pointing up, or to the right if the magnetization is pointing down. And this leads to a transverse voltage, the Hall voltage. And this Hall voltage enables us to detect the orientation of the magnetization or the domain walls. And now we've demonstrated that we can now shrink the width of the racetrack from microns, which is necessary for optical detection, to less than 80 nanometers. And these types of dimensions are relevant technologically. And in this picture, you can see a racetrack. First, we show the optical image on the top left, a single domain wall moving from the right to the left. And then we follow this domain wall moving through this racetrack all the way from one side to the other using a set of Hall bar sensors we've lithographically patterned into the racetrack, which is 80 nanometers wide. And this means that a single domain wall, we can follow its trajectory and prove that it moves without any hindrance all the way along these extremely nanoscopic wires. And at the bottom, you can see the types of current pulses we're using are increasing in intensity from the left to the right as we increase the iteration number. And this is why the domain walls will go faster when the intensity of the current pulse is increased, shown here. Well, this is a very important development that enables us to show the possibility of moving domain walls with current pulses at speeds exceeding 1 kilometer per second in racetracks a few tens of nanometers wide. And moreover, we demonstrated, as shown here, we could position an individual domain wall to an accuracy of a few tens of nanometers, spaced by 100 nanometers along this racetrack. And this, I think, is a very important development that enables us to prove that the nanometer scale domain wall racetrack shift registers can be realized, meaning that basically we're ready for technological implementation of this technology. We've also demonstrated that if we incorporate a tunnel junction reading device into a short racetrack, we can move a single domain wall from one side of the racetrack to the other, detect its where it is, and we can do this in speeds of less than 500 picosecond. This is extremely fast. So we can build a single domain wall racetrack, which has a performance that is as good as the fastest charge-based memory today, static random access memory, but would have a smaller form factor and would be more reliable and, moreover, would be non-volatile. It retains the state without the need for current that would be needed in an SRAM, static random access device. So we've demonstrated now ultra-fast operation, single domain wall racetrack. We've demonstrated we can move multiple domain walls at speeds exceeding 1 kilometer per second in a racetrack to build a multiple domain wall racetrack that would be suitable for replacing a magnetic disk drive with a technology, with a device which we've engineered to be 1 million times faster to access the first bit, to have use 50 times less energy, and of course to have a much smaller form factor and to be totally reliable. So we believe that we're on the cusp of replacing magnetic disk drives with racetrack memory in the near future. So I'm running out of time, but I did want to say, in my institute in Germany, we have several programs to develop 3D racetrack. And I think this is a beautiful example. We've recently published, this is by a student, Kei Gu of mine, in which we use a very elegant technique in which on the substrate, the wafer, we grow first a water-soluble oxide layer. And on top of this oxide layer, we grow our atomically engineered racetrack. Then we dissolve the oxide layer from the edges of our wafer. This is 1 centimeter by 1 centimeter, and the membrane of the racetrack is floated off, and we float it off onto a substrate in which we pre-patterned to have helix, you can see in the top right, up to 1 micron tall. And in the bottom left, you can see the black line in this cross-sectional transmission electron micrograph is our racetrack. It's just a few nanometers thick. And you can see that it follows this hillock we've built into the substrate. And we've demonstrated that the domain walls move essentially with the same performance, the same velocity for the same current density as in the film before we floated it off on water. I think this is a very elegant technique. And finally, we've also developed our own multiphoton lithography system, which has a pixel size 10 times smaller than any commercially available device. And we give some, this is by Andre Farina, another student of mine. And in this, I have to finish now, in this device, you can see just some examples of some interesting devices. These are scaffolds onto which we deposit the racetrack, and this is shown here in this cartoon. If this video works, unfortunately it's not working. You would see the domain walls moving at different speeds depending upon the geometrical portion that we've imposed into this device. So I think I'm running out of time. I will just summarize by saying that the spintronic technologies have, I think, created very interesting means of storing digital data. On the one case, we developed a spin valve sensor that is 1,000 times more sensitive in the detection of small magnetic fields than any other sensor at room temperature, and basically enabled a more than 1,000-fold increase in the storage capacity of magnetic disk drives since this technology was introduced in 1997, subsequently replaced by tunnel junction devices, spin-dependent tunneling, and we've demonstrated that this magnetic random access memory we proposed in 1995 is viable, and since 2019 it's commercially available from all the major semiconductor foundry companies, and has already sold, I'm told, several $1 billion worth of MRAM, which is fantastic. So finally, I'm very excited by the possibility of racetrack memory, a three-dimensional device in which we move the digital information by currents without moving any atoms. This is very important. This makes it highly robust and reliable. And we believe, or I believe, it's now a viable replacement for magnetic disk drives due to its non-volatility, extreme high performance, low energy, small form factor, and high reliability. So I briefly discussed 3 successful spintronic technologies, all based on spin currents that are designed to cross atomically engineered interfaces. And I'm sure there's much more to come in the future. And I thank you so much. Again, I want to thank the National Academy of Engineering for having awarded me the Draper Prize, for which I'm extremely humbled and honored. Thank you very much.
Well, thank you, Stuart, for a fascinating presentation. There's no doubt that the big data world that we live in today was greatly enabled by what you've done in the area of spintronics. We only have a few minutes left if we stick to our original schedule of 60 minutes. So you talked about three-dimensional memories as being maybe the next step. Tell us a bit more about how that progress will flow and when you expect us to actually have those in the marketplace.
Oh, thank you very much for that question. So three-dimensional memories, I briefly discussed this racetrack memory concept. I think now we're on the cusp of transferring this technology, if you like, from the laboratory into the foundry. Now, what this requires, of course, is a very large investment of money, because we only explore individual racetrack devices, quite frankly. Now you need to build billions of them, and that requires a sustained and significant effort to prove that when you build billions of them, the reliability is sufficient to enable an operational technology. But I think this is, I think we, for example, I'm very happy that Samsung in Korea, in Seoul, Samsung Electronics has supported my work in Germany for the last 5 years. And I think they are very happy with the progress that we've made and its potential as a viable memory, whether it's to replace static random access memory, which might be easier than building a three-dimensional racetrack, or one can stack multiplicity of horizontal racetracks to enable a racetrack memory with the same capacity as a magnetic disk drive. So there are all sorts of possibilities on the horizon.
What was the spark that drove your interest actually in the notion of using, in addition to charge, spin as a way to store information?
So, well, I mean, this whole, when I worked for IBM Research, and IBM Research in those days, when I first joined IBM, the research laboratory was on the same campus where IBM manufactured disk drives, 10,000 people building magnetic disk drives. So, of course, there was tremendous interest in having exploratory science in the area of magnetism that could potentially be transferred and used to help advance magnetic disk drives.
So, obviously, one of the things important to any engineer today is the talent that will replace us someday and allow this progress to continue. You spent yesterday, I think, with the Future City competition and spoke with young students there. What advice or words of wisdom would you share with those students to make sure that they maintain and then fulfill their interest of being an engineer?
Well, as you say, it was fantastic to visit Future Cities yesterday. More than 1,000 middle school and high schoolers showing enormous enthusiasm and interest in their projects. And I think what they must do is continue to be excited by the possibilities of technology and engineering to help solve the enormous problems, if you like, not problems, I would call them challenges of today. So I think it's, the advice I would give them is to pursue their dreams of being engineers and to continue to have an inquiring mind, and so as to imagine ways of going beyond what we know today.
Well, thank you for sharing your thoughts, and congratulations on being named the 2024 Charles Stark Draper Prize winner in engineering. We congratulate you on joining a very small group of pioneering engineers whose contributions have shaped the world that we live in today. Thank you for all that you do and have done.
Thank you very
Tonight,
much.
the NAE will present the Charles Stark Draper Prize for Engineering to Dr. Parkin. This ceremony will be webcast from the NAE website from 8:30 p.m. to 9 p.m. Eastern Time. I hope everyone will join us as we continue our celebrations to honor engineers who are changing the world. Thank you and good afternoon.
Thank you.